Hello everyone, welcome to Brain Blitz Audios. Today in this episode of Derivations, we'll be looking at the chapter Wave Optics. It's one of the chapters which is present in the unit called Optics, and it is the 10th chapter in the grade 12 syllabus for physics in CBSE. Wave optics is an entirely new branch of optics that we'll be studying where light is considered as a wave. So in this chapter, we're going to be dealing with some basic concepts and their derivations with respect to wave optics. So the first thing that we're going to prove is to prove that the laws of refraction are true on the basis of the wave theory. So now let's start, deriving and essentially proving the laws of refraction are true. So in order for this to happen, let's draw a plane, say xy, and in this plane, let's say that a wavefront PA is incident, PA, and these are made of incident waves, which are M and L, and the normal in this case is N and dash. Now over here you will notice that this medium is having refractive index N1 and this medium is having refractive index say N2. So refraction occurs. So now we'll consider this to be the angle of incidence, which is equal to I here. And now on refraction, forming a wave L dash, you will notice that there will be an angle of refraction here, say R. Now, as the first part of the wavefront refracts, the wavefront is still propagating. So until the wave M reaches the interface, the wavefront will just keep on moving. So it goes like this until it reaches here. And now from here you have another normal. And at this point P dash, you're essentially moving, you're basically refracting the wave M into the medium 2. So that creates M dash, the wave M dash. And once again, the angle of refraction here is R, the angle of incidence is I. So now what happens is that we can form a separate wavefront based on the refracted wave, which we can label it as P dash A dash. So this is the wavefront in the refracted medium. So when we take a wave, say Q, and this wave is incident on the surface at a point K, and then it starts to refract, and then it hits the refracted wavefront at say Q dash. Now we're going to find out whether the laws of refraction are true in this case. So now let xy be a plane surface separating air from denser medium, and PA be the plane wavefront just incident on it. Let LA and MP be the normals to the incident wavefront representing incident rays. If A and B the normal to refracting surface at A, then angle NAL will be the angle of incidence. When the disturbance, so let's write down from here, when the disturbance from point P on incident wavefront reaches, that means just reaches, point P dash on the refracting surface at xy. So what happens is that the secondary wavelets from point A on the surface will grow into a sphere of radius a dash. So basically we will be having a sphere here. So I'm just drawing one part of it, so just to show the intersection at a dash. So we'll grow into a sphere of radius a dash such that a dash divided by v, that is the speed of light in the medium, is equal to pp dash divided by c. Now from here you'll get a dash is equal to v by c times pp dash. So now v here is the velocity of light in, let's say, okay, velocity of light in medium 2, and c is the velocity of light in medium 1. Let's consider this to be air, so we write the value c. So now let p dash a dash represent the refracted wavefront, and a dash l dash m dash p dash represent refracted rays, and let angle n dash a dash equal to the angle of refraction. So when we look at that, it's somewhere here. So this is n dash a dash, so this is the angle of refraction. So consider any point Q on the incident wavefront when the disturbance from point P on incident wavefront reaches the point P dash. The disturbance from point Q reaches the point Q dash via a point K on XY. So this is the wave that's in the middle. So at point Q, the wavefront's end will be at point P. So when at the instance where P reaches P dash, the point Q, the wave at point Q have undergone refraction at a point K on XY, and now it is at a point Q dash. So since P dash A dash represents the refracted wavefront, the time taken, so the time taken by light to travel from a point on incident to corresponding point on refracted wavefront should always be the same. And this is like the most important concept here. So the time taken by by the light to reach from Q to Q dash will be QK, that's the distance, divided by the speed c, plus KQ dash, which is again distance, divided by the speed, which is v. So now in triangle AQK, the angle QAK is equal to angle I. So if you go back here, let's trace triangle AQK, this one. So angle QAK represents the incident angle, the angle of incidence, and therefore we can write the sine of angle of incidence, sine I, equals qk divided by ak. So qk equals ak times sine of angle of incidence. Now, similarly, in triangle p dash q dash k, which in this case would be p dash q dash k. So since this is the incident wavefront, so we can write this angle also to be the angle of refraction. So that is angle q dash p dash k is equal to r. So therefore sine r is equal to kq dash divided by kp dash. So we can write kq dash is equal to kp dash times sine r. Now remember our original equation, time equals qk by c plus kq dash by v. We'll just substitute the values of qk and kq dash. So qk was equal to ak times sine I divided by c, plus kq dash would be kp dash times sine r divided by v. Now kp dash can be written down as ap dash minus ak. So ak sine of incident angle divided by c plus ap dash minus ak sine basically it's sine r divided by v. So how are we going to represent this equation now? Now this equation can be represented as t equals ap dash divided by v sine r. So basically we are multiplying sine r to both ap dash and ak. So ap dash sine r divided by v, and then plus, we're taking the terms of ak common, plus ak times sine I divided by c minus sine r divided by v. So now let's consider time t is independent of the point k. And it is true because at the same time as a reaches a dash, p reaches p dash, and also q reaches q dash. So the point k on xy does not even matter. So therefore time is independent of k. So since time is independent of the point k, we can write sine I by c minus sine r by v equals 0. So sine I by c equals sine r by v. That means sine I divided by sine r is equal to c divided by v, which is equal to the refractive index mu. So that is a constant. So basically now we can write that the sine of angle of incidence is equal to the sine of angle of refraction. So the sine of angle of incidence divided by the sine of angle of refraction is always a constant. So this is Snell's law of refraction. So basically we've proved that the laws of refraction are true even in wave optics. Now let's look at another derivation. So in here we need to derive the expression for fringe width from the Young's double slit experiment. So basically in this derivation we'll be looking at the Young's double slit experiment in detail. So in the Young's double slit experiment, if we draw the diagram, you have a screen here on the right hand side And on the left hand side you will be having two slits. So the slits are S1 and S2, and their midpoint is Q, and their distance between them is D. So now let's draw normals to the screen from the slits and also from Q. So from source 1 you will be having one light ray hitting a point, say P, and then another ray from S2 also hitting the point P. So this is at constructive interference. And let's say this is A, this is O, and this is B. So now let's consider this distance, the distance between the slit and the screen, the slits and the screen, to be capital D. So this diagram shows that we have to consider two coherent sources of light, S1 and S2, placed at distance D apart, and a screen is placed at distance capital D from the plane of the two sources. Let P be the point on the screen at a distance y from the center of the screen, which is O. So OP is equal to y. Now let's consider x to be the path difference. So if x is the path difference between the light waves reaching at P from S1 and S2, then we can write x to be equal to S2P minus S1P. So S2P is the distance traveled by wave 2 and S1P is the distance traveled by wave 1. So that the path difference can be this difference between the distances of the two waves. So now let's consider triangle S2BP. So in this triangle, it is a right angle triangle, so angle B is equal to 90 degrees. So therefore you can write S2P the whole square as equal to S2B the whole square plus PB the whole square. So PB square can be written down. So let's consider S2P the whole square to be equal to the quantity SB. S2B is equal to the distance between the slit and the screen, so that's D square, plus the distance between O and B can be written down as D by 2. I mean, if you notice, then this is basically D by 2. So OB is equal to D by 2. So therefore, y plus D by 2 the whole square. So that is according to the Pythagoras theorem. Let's consider this as the equation 1. Similarly, in triangle S1AP, Again, angle A equals 90 degrees, so this is a right angle triangle. So according to the Pythagoras theorem, S1P the whole square will be equal to AP the whole square plus S1A the whole square. So AP the whole square can be written down as Y minus D by 2 the whole square plus S1A is equal to S2B, which is equal to capital D, so capital D square. So now let's consider this to be equation 2. So subtracting equation 2 from equation 1, you get S2P the whole square minus S1P the whole square. That will be equal to D square plus Y plus D by 2 the whole square minus D square minus Y plus, it's actually Y minus D by 2 the whole square. So D square and D square gets cancelled, so it's basically Y plus D by 2 the whole square minus Y minus D by 2 the whole square. So this equation is similar to the algebraic equation A square minus B square. So both sides can be, so the left hand side can be written down as S2P plus S1P times S2P minus S1P, and the right hand side can be written down as Y square plus D square by 4 plus 2YD by 2, and then minus Y square minus D square by 4 plus 2YD by 2. Now, S2P minus S1P can be written down as the path difference x. So S2P plus S1P times x is equal to 2YD by 2 plus 2YD by 2 gives you 4YD by 2. So that is equal to 2 times YD. So therefore, the path difference here is equal to 2YD divided by S2P plus S1P. This is an important formula in order to find the path difference. So, now let's consider S2P and S1P to be approximately similar to D. So S2P is approximately equal to S1P, approximately equal to the distance between the slit and the screen, that is capital D. So therefore, x will be equal to 2YD divided by 2D. So the path difference can be written down as YD divided by D, where Y is the difference between the center of the screen and the point P, and D stands for the distance between the two slits, and capital D stands for the distance between the slits and the screen. So now let's consider the position of maxima and minima on the screen. Using that, we can find out the fringe width. So basically, if x is equal to n lambda, then P will be point of a bright fringe. So therefore, you can write down YD by D, that's the path difference, to be equal to n lambda. That means Y equals ND lambda by D, where you can write n as the set of whole numbers. that is 0, 1, 2, 3, 4, etc. So when n equals 0, y naught equals 0. So when n equals 1, y will be equal to d lambda by d. And for n equals n, yn is equal to n d lambda by d. So that is the nth. So this is the formula that we use to find the nth bright fringe. Now to find the dark fringe, so if x is equal to 2n plus 1 times lambda by 2, then P is the center of a dark fringe. So y dash d by d equals 2n plus 1 times lambda by 2. So therefore y dash is equal to 2n plus 1 times d lambda divided by 2 small d. This is the distance for the n plus 1th dark fringe. For n equals 0, y naught will be equal to d lambda by 2d. For n equals 1, y1 will be equal to 3d lambda by 2d. So those are the first dark fringes and the second dark fringes respectively. So knowing the bright and dark positions of the bright and dark fringe will help you in finding out the fringe width. The fringe width is basically the distance between any two consecutive bright or dark fringes. So fringe width beta is equal to the distance between two consecutive bright or dark fringes during interference. So we can write beta is equal to yn minus yn minus 1. So for bright fringes, that will be nd lambda by d minus n minus 1 times d lambda by d. So that will be d lambda by d into n minus n plus 1. So beta is equal to d lambda divided by d for a bright fringe. And then you can always use that to draw the diagram between the distance and intensity of the interference pattern. So this is how the interference pattern would look like. The fringe width pattern would look like on the interference perspective. So basically this will be beta 1, beta 2, beta 3, etc. So this is the distance measured in y. So this will be the first, basically you have a central bright fringe first before the first. So let's erase that. So this diagram is sort of incorrect. Let's draw that again. Basically you have a central bright fringe, then you have a first, then you have a second, then you have a third. And again in the other way, you have a first, you have a second, you have a third. All of them have the same intensity at their highest points. So minus B1, minus B2, minus B3. So this is how the graph looks like for an interference pattern. When monochromatic light is replaced by white light, colored fringes form on either side of the white central fringe in Young's double slit experiment. Now, wavelength of blue light is usually small, so the fringe closest to the central white fringe is usually blue and the farthest is red. Beyond the few fringes, the fringe pattern becomes not clear. If one of the two slits is covered by black paper, there is no interference pattern, so interference requires two coherent sources of light. When the source of light moves towards the double slits, there is no change in interference pattern, but there will be an increase in intensity. So we had two slits, so if the original source was closer, then there will be an increase in intensity, but the pattern stays the same. Now, the important thing is that if this system is immersed in a medium of refractive index, say n, then new fringe width beta dash is equal to beta divided by the refractive index n. So this is how you can calculate the fringe width of an interference pattern in the Young's double slit experiment. Now let's look at the final derivation. We need to find the expression for the width of central maxima in a diffraction spectrum. So diffraction is considerably different from interference. It is a phenomenon of bending of light at sharp corners of obstacles and spreading into the region of geometrical shadow. It is observed if the size of the obstacle is of the order of wavelength of light. So when we're talking about diffraction, and especially the width of the central maxima, we will be using diffraction of a single slit. So that is this diagram. So you have a single big slit, and then there's a screen out here. Both of these are displaced by a distance capital D. And then you have points. Okay, so let's consider this to be A, and you have a point B here. You know, when you're drawing an imaginary line, there will be a middle point called B, and then there will be a point C here. The width of the slit is A, and we will be having a lens, so in this case it's a convex lens, present in the medium. So what happens is that if we take two rays from both A and B, I mean from the three sources, that is A, B, and C. So let's take it from B first so that it will be more clear. So B, the ray from B, it passes directly through without any, you know, diffraction procedures. And the other ray, it starts moving and then it gets diffracted like this. The rays from A start moving down. Okay, so let me erase that. So let's consider that again. So let's start again. So it hits the lens and then it moves towards the point O. And then you will be having another ray from the point A, which moves here and then comes to rest at the point P. So let's draw these arrows, otherwise we'll be confused regarding which wave is what, which ray is what. So now from C, you'll be having the parallel ray, which will be refracted towards O, and then another ray which is inclined, and all of these are inclined at the same angle. If the diagram doesn't make it sense, then I'm just telling that so, because all of these have an angle theta in between them. So this is theta, this is theta, this is also theta, and then the distance between these two can be written as y between O and P. And there will be also an angle between A and one of the rays that is slanted. So when you draw a normal to the ray CP from A, then you'll get another angle that's here. So that angle, which is theta, will be the same as the theta that's found when these lines are incident from the source. So now we consider a monochromatic source of light S emitting light waves of wavelength lambda. So the wavelength is lambda. A plane wavefront gets incident on a narrow slit AC of width A the diffracted light is made to converge on the screen using a convex lens. So let d be the distance from the slit to the screen. The path difference is what we find first, the path difference of light reaching P from two sources A and C is CP, that is this ray, minus AP, that is that ray. So let's say that the normal N is somewhere here. Yeah. So that's the normal. So CP minus AP, that is the path difference, can be approximated to that normal, which is Cn, the distance between the normal and the source C. So Cn would be the approximate distance, that is the difference between CP and AP. Now from triangle ACN, which is this one, you find that sine theta will be equal to Cn divided by AC, where AC refers to the width of the slit, so that will be Cn divided by A. So therefore you can say Cn is equal to A times sine theta. Since theta is small, sine theta can be written as equal to the angle itself, theta. So Cn is equal to A times theta. Okay, so that is the path difference. Now let's look at the essential maximum. At O, the path difference between the rays coming from AB and BC is 0. So you have this ray from A and this ray from B, and then you have another ray from C as well. So all of these have a path difference of 0. Hence the constructive interference takes place. The point O is called as central maximum. So let's write that down. The central maximum is the point O. And this point O has maximum brightness due to the convergence of the rays because of that convex lens present. Now let's find out the position of secondary maxima and minima. So in diffraction, in that diagram, you notice that there is a point P. So consider at P on the screen at which the wavelets traveling in a direction make an angle theta with BO are brought to focus by the lens. So all the angles that have an angle theta would be convergent at the point P. So the wavelets from different parts of the slit do not reach P, although they are initially in phase. So because the problem is that they have this path difference, so there is unequal distance in reaching P. So the wavelet from A and C will have a path difference Cn. So let's write down the path difference first. Cn is equal to A theta. Now let's suppose that P is at such a distance from the center such that Cn can be written as equal to the wavelength, that is lambda. So therefore you can write A theta is equal to lambda, or theta is equal to lambda divided by A. This is the point where you will get your first secondary minimum. Now, in the diagram, we notice that B divides the slit AC into two equal halves. So imagine slit AC being split into two equal halves, AB and BC. Then the wavelets from corresponding points of the two halves will have a path difference of lambda by 2. So that means at AB and BC, wavelength can be written down as lambda by 2. Similarly, the point P on the screen is at such a distance from center such that Cn, that is the path difference, is equal to 2 lambda. That means a theta is equal to 2 lambda, or theta is equal to 2 lambda by A. This is at the point of secondary minimum. So the reason why lambda by 2 is because that K and L are midpoints of AB and BC such that KL is A by 2. Therefore, the path difference is LP minus KP, so that's A by 2 sine theta, A by 2 theta, A by 2 times lambda by A, that is equal to lambda by 2. So that's how the wavelength is halved when you have the slit width getting reduced. So in general, we can write equation for secondary minimum to be theta is equal to n lambda divided by A, where n is equal to 1, 2, 3, etc. So n is the set of natural numbers. Now let P be a point on the screen such that Cn, that's the path difference, is equal to 3 lambda by 2. So that means A theta is equal to 3 lambda by 2, which also means that theta is equal to 3 lambda by 2A. Now this point gives you the first secondary maximum. Now we imagine slit AC split into 3 equal parts. Then the wavelets from the first 2 parts will reach the point P in opposite phase, cancelling the effect of each other. The wavelet from the third part remains uncancelled and produces the first maximum at the point P. The path difference will now be, again equal to 5 lambda by 2. So when Cn equals 5 lambda by 2, then you can write A theta to be 5 lambda by 2. That means theta is equal to 5 lambda by 2A. So the general equation for secondary maximum is equal to, can be written down as theta equals 2n plus 1 times lambda divided by 2a. Again, n is equal to 1, 2, 3, etc., the set of natural numbers. Now let's look at a fringe width. So now let's look at the fringe width in diffraction series, so in the diffraction spectrum. So consider triangle BOP in the diagram. You can always watch back, you can always go back and check the diagram, or you can just refer the diagram that you've already drawn. So over here, tan theta is equal to OP divided by OB, opposite by adjacent. Now OP is equal to Y, OB is equal to the distance D, capital D. And again, since theta is small, you can write tan theta to be equal to theta, so that is equal to Y divided by D. Now remember that for secondary minima, theta is equal to n lambda divided by A, n lambda divided by A. So therefore, you can write n lambda by a is equal to y by d. So therefore, y is equal to n lambda d divided by a. This is the distance for the nth fringe. So the distance for the nth fringe can be written down as y is equal to n d lambda divided by a. Beta, which is fringe width, can be written down as yn minus yn minus 1. So that is equal to d lambda by d times n minus 1, so n minus n plus 1. So that means beta is equal to d lambda divided by the width of the slit, which here is equal to a. Now let's find out the width of the central maxima. So this is one of the main differences that differentiate interference and diffraction. The central maxima, when you look at fringe width in an interference pattern, the fringe width stays the same, but for diffraction, the central maxima is twice as wide as the other, it is twice as wide and twice as intense as the other interference pattern, so the other fringes. So the central fringe is the brightest in diffraction. So you have intensity and you have distance in y. So at 0 you have maximum intensity, so this is your central maxima, and the point of minima can be written down as lambda by a. The next point can be written as 2 lambda by a, and the next point can be written as 3 lambda by a, and so on. And on the other side it's the same, that will be minus lambda by a, minus 2 lambda by a, minus lambda by a, minus 3 lambda by a, and so on. The important thing to note is that the width is different for the central maxima and also the intensity. So over here the graph is a little messy, but when you're drawing an actual graph, remember that the other fringes are not as intense and they are not as wide as the central maxima. So that is the difference between interference and diffraction. So we hope you found this video interesting and informative for wave optics. For more of such useful and interesting content, don't forget to subscribe to our channel, which is Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.